This video is about section 4.2 of Dummit and Foote, which is on groups acting on themselves by left multiplication. So we've talked about this, but let's write it down. So I'm gonna let G be a group, and I'm going to consider G acting on G by left multiplication, like I said. By which I mean if G is in G and A is in G, then G acting on A is just G times A, the multiplication in the group. And we remember from earlier videos that if G is a finite group with order n, this gives a permutation representation G into Sn, which is obtained by numbering the elements of G 1 through n, and then tracking how an element of G acts well on an element of G, but now we're thinking of it as a number because it's been numbered, and where what number is being sent, what number it is sent to. And we remember that this particular permutation representation is actually called the left regular representation. Left regular representation of G. Okay, just repeating the vocab so that it sticks. Now, important facts about this particular action. It is always transitive, which we remember means that there's only one orbit of the action of G on itself, or alternatively, for all A1, A2 in G, there's G in G with G times A1 is equal to A2. And it's easy to find this G, right? This little G is just A2, A1 inverse, if you check this multiplication. And of course, A2, A1 inverse always exists by the axioms of a group. So it's always transitive. It's always faithful. Which we remember means that the kernel is trivial, and the kernel of the representation we can think of as the kernel of this group homomorphism, or as the elements of G that fix everything. And that's because if G times A is equal to A for all A in G, then G has to be the identity. In fact, if G times A is equal to A for 1A in G, then G has to be the identity, because you can just multiply both sides by A inverse. So G is equal to 1. Okay, so the action of G on itself by left multiplication is transitive and faithful, and kind of following from what I said here. Here I said, well, okay, so I kind of got ahead of myself because I got excited, right? Here, when I was talking about the kernel, I was saying, oh, if GA is equal to A for all A in G, then G is trivial, and I was like, even if it happens to only one of them. And so actually, if you consider only one of them, this means that the stabilizer of A, which is also denoted G sub A, is 1 for all A in G, right? No element. So we're back to the situation, right? I'm trying to think if GA is equal to A, G has to be 1, even if it's just 1A, right? Here I'm thinking about for all A, but actually I said for only 1A, it would still imply that G is equal to 1. So here I'm saying, okay, if you fix 1A, like one element of G, what can you be? And you have to be the identity. Okay, so that's cool, but we can generalize this, and since we're mathematicians, we will. So I'm going to let H be a subgroup of G, and now I'm going to have G act on the left cosets of H and G. The action will be G acts on the coset of A by just giving me the coset G of GA. The left coset of GA in H. So again, a kind of left multiplication, but now it's a left multiplication on cosets of H instead. This again, this is transitive, so this action is transitive. For the same reason as the action of G on itself is transitive, because using an element of G, I can get to any element in G, well, certainly I can get to any coset. So action is transitive, but it's not faithful. So it's not faithful. The kernel of the action is this group, the intersection for X and G of all the conjugates of H. So you take an element of G, you do X, H, X inverse, and you intersect all of these. Now, this is, in fact, the largest normal subgroup H. It should make sense to you that this is normal because it's the intersection of every coset. So if an element is in this intersection, it's the intersection of every conjugate. So if an element is in this intersection, all of its conjugates also have to be in the intersection because we just intersected. The things that are left belong to a conjugate of H for every element of G. And maybe that doesn't make sense. I mean, maybe you're like, I kind of see it, but I kind of don't see it. I highly recommend just pausing this video for a minute and working it out. It will make you feel so much better and smart and happy. And the last thing that I want to say is that the stabilizer of the coset 1H, right, just a coset H, is just H. So the only thing that fixes the coset H, right, if you want to say G times H is equal to H, this is if and only if G belongs to H. That's the only way. So that's just saying that here. So with this being said, in this section, there are a couple important theorems. So I just talked about acting on subgroups, but now I will go back to G acting on itself, right? So we had G acting on itself, and then we're like, actually, G can act on subgroups, which is cool and more general. Sorry, not on subgroups, but on cosets, left cosets of subgroups, which is nice and certainly does come up. But now let's go back to G acting on itself and talk about Cayley's theorem, which, if you're looking for it in the book, is corollary 4 of that section, which says that every group is a subgroup, is isomorphic to a subgroup of a symmetric group. And that's via the left regular representation. Because the left regular representation is a map of G into a symmetric group that has trivial kernel. So by the first isomorphism theorem, the image of G is isomorphic to G. And so the image of G is a subgroup of that symmetric group, and that's isomorphic to G. And in particular, if G is a finite group and the size of G is n, then G is isomorphic to a subgroup of Sn. This is pretty interesting, on its own, because symmetric groups are very concrete. They do, they just move numbers around. But it's also interesting historically. The only groups that were studied were permutation groups, which are subgroups of symmetric groups. So literally groups that permute things. And with the left regular representation, we see that actually every group is a permutation group. So when they were seemingly studying, only permutation groups, they were actually studying all groups. They were not missing out on anything. Now, a very important result that comes up all the time in qualifying exams is corollary 5. And it's so important, I'll just make a line and take a little bit of time so you have time to really ready yourself for this. So this is a mere corollary, but so useful. So if G is finite, a finite group of order n, and P is the smallest prime dividing n, and H is a subgroup of G such that the index of H in G is P, then H is normal. I want to make a remark before I sketch the proof. Okay, note, such an H might not exist. Might not exist. Okay, so if P is any prime dividing n, there's a subgroup of order P. But here I'm talking about a subgroup of index P. That might not exist. That's not guaranteed by anything. But if there is a subgroup H of index P prime, and P is the smallest prime dividing n, so that's pretty restrictive, but qualifying exams always find a way to make use of this, then this group has to be normal. It doesn't have a choice. And the way to prove this is via the action of G on the left cosets of H. Okay, so proof via G acting on the left cosets of H. So this gives us, a map, homomorphism, G to the symmetric group on P symbols, because the size of G mod H is P, because that's equal to the index of H in G. Okay, so we have a map, right? G going into SP, and I'm going to let K be its kernel, and K is contained in H because we talked about how that was actually the largest normal subgroup of H. So in particular, it's just in H. So say that the index of K in H is this number little k. Okay, then if we want to know the index of K in G, well, you can do that in 2 steps. You first, count the index of H in G and then the index of K in H. So that's K times P. Now, we do have that. So now we consider the map G mod K going into SP, which is just this map, but now we've modded out by the kernel, so it's injective, right? injective because modded out by kernel. Okay, so G mod K, again by the first isomorphism theorem, is isomorphic to a subgroup of SP. And so, in particular, the order of G mod K has to divide P factorial, which is the order of SP. Okay, because we know that the order of a subgroup always divides the order of the full group. Now, this number, the number of left cosets of K in G, is the same as this number, the index of K in G. And so this means that Kp divides P factorial. And we can divide by P on both sides. That implies that K divides P minus 1 factorial. So now, this means that K has to be some number that's strictly less than P, right? Because, P minus 1 factorial is 1 times 2, all the way to P minus 1. There's no primes that are P or greater dividing that. But P was the smallest prime. Dividing the order of G, and K certainly divides the order of G. The index of any subgroup divides the order of the group. And so if K needs to be, some number strictly less than P, but it also needs to divide the order of G, and P was the smallest prime dividing the order of G, the only way this can happen is if K is 1. So remember that K was the index of K in H, so that's 1. So H is equal to K, but K was normal in G because it was the kernel of some homomorphism, so H is normal in G since it's the kernel of a homomorphism. So that is pretty cool. And that actually is everything that was in the section. So that's it for this video.